Hi, so today I want to talk about after we've gotten off the ground with the definition of the derivative, which there guarantees that the derivative is the slope of the tangent line like we want it to be. We prove all of these wonderful rules that make it so much easier to calculate derivatives, right? The power rule, the chain rule, linearity, product rule, quotient rule. In this video, I'm not going to go through each of these rules and explain why they're true. I'm going to take all of these as given, and I just want to show an example of how you would use these, especially how you would use multiple of these in tandem in practice when you're actually calculating a derivative. So to see some of these in a rather complicated function all being used together, let's look at, for example, suppose we're given the derivative of sine and cosine, right? These are ones that require special limits, right? So say we have the derivative of sine as cosine and cosine as negative sine. Say we know these derivatives, right? So given these, let's find the derivative of, let's do the tangent squared. Let's say I wanted to find this. Right, so that's the function I want to find the derivative of. So tangent squared, how can I find tangent squared if I only know the derivatives of sine and cosine, and if I also have these rules to play with? Well, here's what I could do. I could take tangent squared and say, all right, this is something I can apply chain rule on, right? I can think of it as an inner function, tangent, and an outer function, square, right? And I can say, what's the derivative of my outer function? Well, I use power rule to differentiate my outer function, right? So this is, and notice this is not a prime that I wrote there. This is a 1, right? So that's my first step. This would be a power rule with my outer function being squaring, right? So that's what I applied right here. This is power rule with n equals 2, right? But then what does the chain rule tell you to do? The chain rule, so I already used the power rule. Now the chain rule tells me to take the derivative of the outer function, which I did, leave the inner function alone, which I did, right? That tangent, I just copied it down. Tangent of x is still tangent of x, my inner function. But then multiply by the derivative of the inner function. So I need to multiply by the derivative of tangent. And if that's something you have memorized, perfect, great. You can just do that, right? Just use the fact that you already know the derivative of tangent. But say you don't. Say I'm really just working off the fact that I know that only the derivatives of sine and cosine here. Well, then what I could do is I could rewrite tangent as a quotient of sine and cosine. And I could use the quotient rule to evaluate this next derivative. So I can say this would then be what? It would be, how do you do quotient rule? You do the derivative of the top times the bottom minus the top times the derivative of the bottom, all divided by the bottom squared, right? This is what I see right there. That's my quotient rule. So let me apply that. So I do the derivative of the top, which is sine, right, times the bottom, minus the top times the derivative of the bottom, divided by the bottom squared. This then is what? I have cosine squared x plus sine squared x, because I have a double negative, all over cosine squared x. So this becomes 2 tan x times what? Cosine squared plus sine x squared x is just 1. And the reciprocal of cosine is secant. So I get 2 tan x times secant squared of x. So there we go. There I have the derivative of tangent squared. And I used nothing but the fact that I knew the derivatives of sine and cosine, right? Also, well, that's not entirely true. I also used the derivative of x squared as 2x to the 1, right? I used the power rule. Well, my base derivatives were just sine and cosine, and then I used all these properties up here, right? I used the power rule, I used the chain rule, so power rule, chain rule, and quotient rule, right? I used all of those properties together. So there's a little example showing those 3 properties all in the same problem, right? Use all 3 of those to get the derivative of tangent squared. So now let's do one that uses the other two, right? Linearity and product rule. So how about this? How about if I had this derivative? What if I wanted the derivative? Find f prime if f of x equals, let's do x minus x e to the x, right? So what would I do? I would say, first, I'm going to apply linearity. What is linearity? It says that I can distribute derivatives across sums. And I can factor out constants when I do this, right? That's what linearity says up here, right? It says if you have separate terms, go ahead and take the derivative of those functions separately. And as you do it, you can also just keep the whatever a and b are there, just keep them out front. So what are the a and b here? The a and b are 1 and minus 1. So that's why I'm just keeping a 1 and a minus 1 as the constant, right? So this first step, I'm using linearity, right? Now after this, I can use here just power rule, n equals 1, right? So, or don't even use power rule, just say it's the derivative of the function x, right? X has slope 1 because it's a line with slope 1. So there you can even just do by geometry, but you can also think of it as power rule with n equals 1. Then we can use product rule on this expression, right? So what would product rule look like? The derivative of the first times the second unchanged plus the first times the derivative of the second. Derivative of x, once again, is 1, right? The derivative of e to the x is e to the x, right? It's itself. So here I get 1 minus e to the x minus x e to the x. That would be my derivative. Now, a very easy place to make a mistake. Be careful. Here, we had that minus 1 outside of that expression before we took its derivative, right? So when you do the product rule and you get two terms, remember to distribute the minus sign. Very easy place to make a mistake. So, all right, so there we go. There's linearity and product rule, both in the same problem. So I just wanted to show two quick problems just to show how these rules all mix and mix and match when you're taking derivatives. Great, thank you.